That's like yeah, look at tax first, I have back.
Oh, that's not. Yeah.
What is this? But like,
What's the hardest?
five. Yeah, like Ethiopian. It's supposed to be, it's basically like reading. It's like, it's like a real place. Yeah, it's
Yeah, I still don't know.
like, you know, the same. That's good. You ready?
Yeah, exactly.
We're down.
Yeah.
Oh, yeah. It's not.
So we're going to start Unit 2. Obviously, it won't be on the test tomorrow. Your test tomorrow is just over limits. Now, 2.1, we kind of already covered tangent line equation, average velocity. So I'm going to skip over this, but your homework will still be what you see here. But I think we covered this at the very beginning of the last week when we talked about average versus instantaneous velocity. Basically, just slope between 2 points and creating your tangent line equation using point slope form. So I'm going to skip over that. I'm going to start with 2.2, limit definition of a derivative. I'm going to be a little bit ahead in the calendar, but I'm not going to change the test date. So that means, if we can get to everything a day early, then we'll just buy an extra day of review, right? So I'm not going to change the calendar even if I'm ahead, which means that the homework assignments is also going to not change as well. So if I'm a day ahead, your homework assignment will still stay the same as what you see on the calendar. But before I jump in, let me kind of highlight a few things I have up there on the board. Just a couple of reminders about your test for tomorrow. First, no calculator. And second, the trig that you're going to see on your test, know your unit circle values. Right? You do direct substitution for limit x approaching a real number. I want you to be able to evaluate that limit. So make sure you review that. And then in terms of being able to recognize graphs, just sine and cosine graphs. Okay, just know how your sine and cosine graphs look. Your unit circle values will basically help you create a picture of that sine graph. No squeeze theorem. We didn't really go over it, but the process is that you're always going to be given a lower, a middle, and upper function. That relationship will always be established for you. And you're always finding the limit of the middle function, because the middle is always going to be the one that's unknown. And you're going to find the limit as x approaches whatever the value is for the upper, middle, and the lower. But only the upper and lower can be conclusive. And we can find the limit by squeeze theorem if the upper and lower are in agreement. If they're in agreement, then there's no choice but for the middle to also share that same limit. If the upper and lower are not in agreement, then we should have to say that our limit is inconclusive, or squeeze theorem is inconclusive, and we don't know what the limit as x approaches 2 of f x is, or that the limit is inconclusive as well. Okay. So there's only two conclusions that you can reach with squeeze theorem. Either you know the limit or you don't. All right, and then there's one more that I want to go over, which is with absolute value function. I'll go over this particular one, and then there's also another one that looks like this that show up on the test review in your packets. So I want to go over this so that you guys can practice it tonight, and I can also go over it tomorrow. So let me go over this particular problem here. This is a limit problem that involves absolute value. So I'm just creating this from scratch, and then you guys can either write this down or just kind of follow along. So the idea is that we want to plug in 3.9, but it's maybe kind of hard to know exactly what's going on here. And if we can sketch a graph or get something that is a little bit more helpful, because the absolute value function kind of feels a little strange, or it's not as clear as we would like. So let's do this. Let's step off to the side and just think about what the absolute value of x minus 4 looks like. This is a function, this absolute value function, with the vertex at where? Okay, yeah, 4. Whatever causes the inside expression to be 0 is your vertex. And your absolute value function is going to be a V-shaped graph. Okay. Now, absolute value function can always be written as a piecewise function, meaning that we can think of this V as the combination of two linear graphs that are meeting at that vertex. There is a linear equation with a positive slope. There's also a linear equation with a negative slope. And they're both getting cut off at a certain point because we don't see the entire two lines showing. So let's talk about the positive slope first. There's an x minus 4. But this x minus 4 linear positive slope graph is only living to the right of 4. There's also a negative slope version of x minus 4. So I'll do a negative parentheses x minus 4. And that is existing to the left of 4, so I say x is less than 4. Now, this vertex point is defined. Both these functions define the point at 4, 0. So we just want one of them to define it, not both. So it doesn't matter which one you choose. So you can put the equal sign either above or below, as long as one of them can take care of that point. Now, this is only representing the numerator portion of our function. So to build the entire function, we know that what we really want is absolute value of x minus 4 divided by x minus 4. But this is only representing the numerator. So to create the denominator as well, let's just divide by x minus 4 to our piecewise function. So now we have something equivalent. But the nice thing here is we can actually clean up this numerator, or these fractions here. What's x minus 4 divided by x minus 4? 1, which is a horizontal line, right? And then what's negative parentheses over x minus 4? Negative 1. So now this feels a little bit easier to read, because limit as x approaches 4 from the left of 4, like 3.9, 3.99, 3.999, that's all going to be within this interval, and it's just going to approach negative 1. So this is just negative 1. So we can read the one side of the limit from the piecewise function. You can also graph it and then read it from the graph, because there's a y value, y equals 1 to the right of 4. There's also a y equals negative 1 to the left of 4. And if I want to approach 4 from the left side of 4, that means I'm picking a point to the left of 4, and I'm following my graph towards 4, and that's holding at a steady y value of negative 1. So that's also my limit. Okay, does that process make sense? So there's a similar problem like this on the test review, so you guys can practice that process now that we've gone over it. Right. Any questions about the test tomorrow? So encourage you guys to go through the test review if you haven't already done so. Tomorrow morning, I will have a help session, 7:15, but I'll also send a Teams link through Remind where you can join virtually. All right. Anything else? Okay. I think if anything else, I'll. Okay, but let's go into our notes for today. Oh, there is homework tonight, but the homework for tonight, I'll be checking on Friday. So tomorrow you guys taking the test, I'm not checking homework. So tonight's homework will be due on Friday. But we're just going to jump directly into 2.2 for notes. Sorry, the calendar and the first page is not in order. So our goal is to discover a formula that can calculate the steepness of all tangent lines to a curved graph. We know the slope of a secant line. And the slope formula requires two order pairs. Because I need to have 2 points in order to have an idea, what is my rise and what's my run, rise over run. So the algebra requires 2 points for slope. But if I want to find the slope of a tangent line, the issue is that this is a tangent line, right? A tangent line that goes through point P. The issue with tangent line is that tangent line, it only skims the surface of the graph at one point. And how can we find the slope if there's only 1 point involved? But slope formula requires 2 points. So that's the problem that we're going to be trying to solve with today's lesson. Like, how do we get to a slope of a tangent line if the slope formula requires 2 points? Okay. What we can do, though, is we know that we can start off with a slope of secant line. Okay. So we're going to find the slope of this secant line. But we know that the slope of the secant line is not the slope of this tangent line. But we can say that it is some approximation of the slope of the tangent line. Obviously, not the same steepness. You can tell the secant line here is more steeper than the tangent line. But we can let that be a starting point. This is not a very good approximation, but it is some approximation for this tangent line. So the idea is, well, maybe I can make an improvement on that secant line slope. And what if I were able to move that point Q closer towards point P? What's going to happen to my approximation of my secant line slope if I were to move point Q closer to point P? It'll be better, right? If my points are closer to each other, you can see that if I were to pick a Q2 or Q3 that's closer to my source of my tangent line, I can begin to see that my slope is going to begin to become more and more accurate. Right. So that kind of begs the question to say, well, what if I can just move point Q so close to point P that it eventually disappears?
then technically I should be able to reach the exact slope of that I want of my secant line. And so this is where we're going to kind of involve limits from the previous unit, is that what if I can shrink the distance between the 2 points to virtually 0, and then that will help me guide me to figure out what the slope of the tangent line is. Okay. So we're going to basically, we're going to start off with the slope of a secant line, but we're going to use the limit notation to help us decrease the 2 points, the distance between the 2 points, until there's virtually no distance between it. And then we get it down to just one single point. Okay, so that's the big picture here. I'm going to go through the process involving getting us to the limit definition. It's going to feel a little messy because we're going to have all these variables to allow for the flexibility of movement between points. But if we just kind of keep the big picture in mind, that I'm just starting with slope, and I'm just going to create a situation where I can move the 2 points closer towards each other. Okay, so I'm going to use this second diagram here to arrive at these limit definition, which is really just a variation of the slope formula. Okay, we have point P here and point Q. And let's start off by creating an ordered pair in function notation for both these points. So point P is at some x value. And let's just say that point P is x comma x of x, f of x, right? Now we want point Q to be some distance away from point P, and I'm going to let that distance be called h. Eventually, we're going to shrink that h down, but let's just give it some certain distance away. So if this is x, and I want to be h units away from x, what is my new x value going to be over here? X plus h, right? So imagine this is 2, and then plus 3, that ends up being 5. But we're letting variables hold that place. We want that flexibility to be any point at all. So let's just let the x value for point Q to be x plus h. So if I plug x plus h into the function, what's my y value representation going to be? Good, f of x plus h. So rather than saying 2 comma 3 and then like 5 comma 6, we're holding on to all these variables to allow for this to work for any situation. Okay, but we're basically just creating 2 ordered pairs. They're just some distance away from each other. That's all this is doing. So let's just let's call this x1, y1. Let's call this x2, y2. And let's just find the slope between these 2 points in function notation. Change in y over the change in x. So y2 minus y1 would just be what? Good. All over. Minus x plus h minus x. Right. Is there anything that can clean up within this expression? Cancel the x's, okay. So this is slope formula, basically. We can do a little bit of cleanup. So that change in x is not as apparent with the x's canceled out, but we can kind of see where this is coming from, right? This is basically just slope formula between 2 points, right? But the flexibility of any 2 points some distance away. So now we're going to talk about shrinking h, right? If I can shrink h down, point P will get closer to point Q because the horizontal distance will decrease, and therefore the vertical distance will also decrease. So we're going to say this. The limit as h approaches 0 of f of x plus h minus f of x all over h. So we're decreasing the distance between the 2 points until there is no distance between the 2 points and point Q falls into point P. And what we're going to achieve from that is we're going to find the exact slope at point P, basically requiring only 1 point because we started with 2 points, but then the second point disappeared into the first point. So this is basically a more robust version of the slope formula because we're actually able to find the exact steepness at a point rather than picking 2 points really close to each other, which will only be an approximation. Okay. And that's going to lead us to what we call the general limit definition of a derivative. And I just want us to recognize this notation as basically a slope formula in terms of variables, right? We built it from scratch, and now hopefully we can see, oh, this is just slope formula, but I'm just allowing that second point to disappear into the first point because the distance between the 2 points is eventually going to reach 0. Okay. There's also this alternate definition of a derivative, which we'll also practice. This one is a little bit more apparent because you can kind of see that change in y over change in x a little bit more clearly. But these both allow us to get to the slope of a point at a curve, or a slope of a curve at a point. So here's the notation. F prime, if you see that little apostrophe there, that we read it as f prime of x. And this is the notation for the derivative function. And derivative is just a fancy word for slope. It's the steepness of a curve at a single point. So the derivative function is a slope finding formula for a curved graph where the slope of the curve is ever changing. So if I were to ask you, what is the slope of a line? Would you be able to give me a number? All we need is 2 points, right? You find the slope of the line. Is the slope ever going to change along this line? No. What if I were to ask you, what is the slope of this curve? You would say where, right? Because every point on the curve, there's a changing slope. But what we can do is we can come up with a formula that will tell us the pattern of the ever-changing slope across this curve. And that's going to be the benefit of calculus is that we're able to do something that algebra is limited in doing. Because algebra, we can find an approximation for every single point in terms of the curve, in terms of slope, but it's very inefficient. But now we're going to be able to find a formula that we can find where we can find the slope at every single point, not just an approximation, the exact slope at every single point along this curve very efficiently, and allows us to solve problems that would be difficult to do with just algebra. Okay, so that's the big picture. Okay, next page. Sorry, whole page is over. Now, building the derivative value or function is going to feel a little bit tedious right now, but it's not going to always be this way. Right? The reason why we're doing it this form is because we need to first establish that there's a connection between limits and slope and derivatives. And after we get past that connection and that relationship, we're going to move to a much more efficient way of finding derivatives. But that more efficient way is more abstract. We can't quite see the relationship as easily. So that's why we're kind of building that relationship now. But once we can understand, oh, slope is derivative slope, then we can move to a much more efficient way of doing it, and also more abstract because we already know the connection between these two. So, once we learn this method, we're going to largely abandon it. I mean, we're still going to need it for the AP exam, and there's certain ways that AP exam can ask about the limit definition. But, if it feels really tedious, just know that it's only temporary. Okay, we're going to have a much more efficient way to do this. Okay, so example one, we're going to find the general derivative of this function x squared. So I have a graph of x squared here. Let me put that. We're going to come up with a formula that's going to allow us to figure out the steepness of this curve at every single point along this curve. Okay. And we're going to do that by getting this numerator out of function notation for this particular function. So off to the side here, I'm going to say f prime of x is equal to, and I'm going to start building my limit notation definition for this function. Now, x squared can replace f of x. That's an easy replacement. But what is the replacement for f of x plus h for x squared? So we know f of x is x squared, right? And if I just have a reserved spot for where that x is, this is basically going to be the place where I can put in my x plus h. So f of x plus h, all it means is I am inserting x plus h into wherever the x is. If it was f of 2, I would plug 2 in for x. If it's f of x plus h, I'm going to replace x with x plus h. So my function notation for f of x plus h for x squared is simply x plus h squared. So f of x plus h is just x plus h squared minus f of x. F of x is just x squared all over h. Sorry, I forgot to put the limit notation in front. Limit as h approaches 0. Now, this goes back to a limit problem where we're approaching a real number. So if we're evaluating a limit where we're approaching a real number, what's our first step? Direct substitution. The only thing that's different here is that x is not the variable here, it's h. X is just some unknown value, but it's just h that we want to replace. So if I replace h for 0, numerator, I get what? X squared minus x squared, which is 0. And my denominator is 0, which tells me that there's a what? There's a hole. Well, so we're going to clean up the numerator. Hopefully, we can get an h to appear in the numerator and we cancel out and then reevaluate. Okay, so we're just finding a common factor that we can cancel out. But there's not factoring that we can do. We're just going to expand it out and see if we can get an h to appear. So FOIL this out. X plus h times x plus h, which gives me x squared plus 2xh plus h squared. Okay, continue cleaning up. Anything that can cancel out here? X squared. Anything that I can factor out here? H. And that is going to be the key to help us finding that match that we're looking for between numerator and denominator. If I factor an h in the numerator, what's left? Plus h. Okay, what can I do now? Cancel out the h's. The hole has been removed. We're no longer going to get that 0 over 0. What's our final step? Reevaluate, right? Replace h with 0. What are we left with? Just 2x. So that is our derivative function. So let me talk about what this is telling us. So if I were to ask, what is the slope of this curve? You know that you can't say a number because it's ever changing. But the slope of this curve is 2x. Question? Oh, it stays with you until the very end. Or it's f prime. Yeah, f prime stays to the very end. So if it's a slope of a line, you can say a number, right? 3 or 5 or -5/3. The slope of this curve is 2x. What that means is this curve has a slope that is changing at this rate, at this pattern, 2x. So let me show you what this can do for us, or I know why this is so useful and so powerful. Now, let's just make some general observations, right? If I were to ask you, without knowing anything about this curve, what do you think the slope of the tangent line is through this point? What does that slope look like? The slope is 0, right? The steepness is 0. There's no steepness. It's just slope 0. Okay, so we know that at x equals 0, we're predicting a slope 0. What about at x equals 1? What do you think that slope could be? You know, it's going to be some positive number, right? Probably not very steep. Let's just say 1 question mark. What about the slope as we get further and further away from the x-axis or from the origin? Still positive, but it's going to be what? Increasing, right? So maybe 3 or 4, I don't know. We know it's going to get steeper, right? What about on this side? What's the steepness at this point on the curve? Negative, but -1, right? Maybe, right? What if we are further and further away? Decrease, a steep, but a negative steepness, right? So maybe like m is like -5 or -6. We don't know, right? Now, what we're going to do is we're going to plug these x values into the derivative function, and this is going to tell us the exact steepness of every point on this curve. So let's just test it out to see how this can be used. So let's say I want to find f prime of 0. My formula is 2x here. So if I were to plug 0 into x, what am I going to get? 0. So that matches with what we know to be true. F prime of 0 equals 0. This is telling us that the slope of this curve at 0 is exactly 0. Okay, that makes sense. We're convinced of that. F prime of 1, I want to find the exact slope of this point on this curve. F prime of 1, by the formula, 2 times 1 is what? Wait, 2. So this is, our approximation was a little bit off, but we can be convinced that this is a steepness of 2. What if we want to go further out? Let's say f prime of 5. You expect a positive slope that is steeper and steeper. What does the formula tell us? 10. And that's the exact slope. Now, everything on this function is symmetrical, right? So we should get a very symmetrical slope if we were to go the other direction. So f prime of -1 will give us what? -2. That is consistent, right? We expect f prime of 1, f prime -1 to be symmetrical. So 1 is +2, the other is -2. That makes sense. And let's just go further and further out. Let's say f prime of -10. We expect this to be even steeper than f prime of 5, but in a negative direction. So if I plug -10 into my slope formula, I get what? -20, and we can be convinced of that as well. That makes sense because we expect a negative slope, steeper than this, but in a negative direction. Okay. So it's nice having a slope formula that can tell us every single slope on this curve without having to painstakingly go, pick 2 points and do the algebra and then do an approximation. That just takes forever. We now have a very efficient way of getting to the steepness of this curve. Now, every curve is obviously going to have a different pattern. So every curve has its own slope formula or derivative that we can arrive at for that particular function. Okay. Now, I want to also establish something is that f of x is x squared, f prime of x is 2x. f of x gives us what on the graph? If I were to plug in a 1 or 2 or 5, what does that give us on the graph? Give us the y value, right? But if I plug the same point into the derivative, I'm going to get what? The slope. Okay, so I want to establish something here. Your function and your derivative function, they both give you information about the same graph, but they give you different information, right? Your function is always going to give you a location or the y value of that original graph. But your derivative is going to give you the steepness of the curve at that point. Okay. So the furthest that we're going to have to go is f double prime, which is going to be is going to give us some additional information about the curve, but we're not going to go past that. But we do need to make sure that eventually that we can know what we're talking about. F of x, f prime versus f double prime, they all may refer to the same graph, but they're all giving you slightly different information about the graph. All right. So your function will give you order pair, your derivative will give you slope, your second derivative will give you what we call concavity, which I think you guys talked about last year if you're coming in from AP Pre-Calc. Okay, so for part A, we found the derivative of our function. And now part B, it says write the equation of the tangent line at x equals 1. So we basically want to figure out what is the exact tangent line equation of this line that you see here. So if I want to find the equation of tangent line, I need point and I need slope. So for part B, we're going to find the equation of tangent line. At x equals 1. So I need to find order pair and I need to find slope. How can I find order pair? I'm going to plug 1 into what? Function or derivative, if I want to find the order pair. Function. Function gives you location, right? So f of 1 is equal to 1 squared, which is 1. So I have an order pair, which is at 1, 1. That point is 1, 1. Now, if I want to find the derivative at that same point, I'm going to plug 1 into the derivative function. So f prime of 1, like we said, is equal to 2. So that's my slope. My slope is 2. So your order pair comes from your function, your derivative, your slope comes from your derivative. You pull your two sets of information, and then you can take it and put it into point slope form. Oops, y minus 1. Order pair is 1 here. Leave your equation in point slope form. This is sufficient. There's no need to get it into slope intercept form. You can, but this is acceptable, so we'll leave it like that. Any questions so far? So here's kind of the big picture that we're going to do for a while is we're going to have a more efficient way of getting from a function to the derivative. But right now, we're going to spend today and Friday, just kind of practicing these function notations or this limit definition of a derivative. But once we learn our more efficient form, then we're just going to be finding the derivative of different types of graphs. And then ultimately, a lot of problems is just, find the equation of that tangent line. So we're just going to be spending a lot of time building the derivative for different functions. Okay, and that's going to kind of take a big chunk of this first portion of first semester. We're just building derivative. Every function has a different curve, different pattern, and so if we want to find the derivative function, it's going to be specifically built just for that graph, right? And then we're going to be just building derivatives for more and more complex functions, and then finding tangent line equations. That's going to be a good chunk of our time. Okay, part C, write the equation of the tangent line of the same function at x equals -5. So we're going to use the same function, the same derivative, find order pair, find slope, and do point slope form. Okay, so basically, we're essentially trying to find the equation of a line that's over here, if this was x equals -5. So see if you can use your function and your order pair to get the appropriate information that you need, and then put in the point slope form, and it'll look very much like this form that you see here. Okay, so try that. Okay, what's my order pair at this point? -5, -5, 25, right? Okay, yeah. So we have so this point is really, really high up on the y-axis, or on the up on the y value here. And then what's the steepness of this point on this curve? -10, because you simply plug -5 into the function, into the derivative, sorry. 2 times -5 is -10, and then you just put in the point slope form. Yes. Yes, that's right. There's a lot of ways to represent the derivative notation, and we'll talk about a lot of them. But yes, there's a lot of different ways. If it's f, you can call it f prime. If it's y, you can call it y prime of x. You can call it y prime. There's all these different notations, and we're going to get to all of them. But yes, there are numerous ways to represent the derivative notation. Okay, so we found our derivative, or sorry, our order pair to be -5, 25. So maybe a point that looks like this. Maybe it's not scaled correctly, but that's the idea. Our slope is -10. You can expect that as you move further and further away from the origin, that your steepness of your parabola is going to get, it's going to create a larger negative value. So then you have your order pair and your slope, put in the point slope form. You can leave it in this form, and this is essentially describing the equation of this line here. Okay, a few minutes here. Let me just see if I can kind of get started with, there's also this alternate limit definition of a derivative, which I want to go over with you. So next page. Actually, let's do this. Let's do the general definition of this new function. Get some more practice with general derivative, and then on Friday we can pick up with the alternate definition. Okay, so let's just get more practice with general definition. So it says find the general derivative of root x. So we first have to get the numerator of our definition out of function notation and for this particular function. So f of x plus h, all that's doing is replacing every x you see with an x plus h. So you're just removing the x and putting the x plus h, and that's going to be your f of x plus h. So let's go ahead and write out our entire definition here. So f of x plus h, we're just replacing the x with x plus h there. Minus, what's my f of x? Just root x, just the original function, right? Now, every time you do this, it's always going to end up giving you 0 over 0. There's always going to be a hole. I'm not going to give you one where, oh, it's going to be a vertical asymptote or continuous function. If you go through this definition, it's always going to give you 0 or 0, but I still want us to check and confirm that there is a hole before we move forward. So if I replace h with 0, root x minus root x is 0, 0 over 0. So what's our strategy to get that numerator cleaned up? By the what? Conjugate, yeah. So conjugate means you're going to copy the exact numerator that you see here. You're just going to change the sign between the two terms. Expand the numerator, leave the denominator alone. Let's do some cleanup here. What do you notice in the numerator? X is canceled out. I'm left with h over h. What can I do there? Also cancel out. This is what we want. We want the holes to go away. There's still a what left over up top? 1. So if I replace the remaining h with 0, what am I going to get? One over what? 1 over 2 root x. Now, this is basically going to tell us how the steepness of this curve is changing across this graph. So that's our derivative function. F prime of x is equal to 1 over 2 root x. This is going to describe the steepness pattern of your y equals root x. Y equals root x looks something like this. So every point along this curve, whatever number you get back in return is going to tell us how steep the graph is. So then it says, write the equation of the tangent line at x equals 2. I need to find the point. I need to find the order pair, and then point slope form. Okay. How do I find the point? Plug 2 into the original. How do I find the slope? Plug 2 into the derivative. Good. And you can leave your answer in point slope form, your equation in point slope form. It's a process. You can also test the decimal value and convince yourself where you know what it could be. Yeah. All right, so tomorrow morning help session 7:15. I'll send out a reminder tonight about your test for tomorrow. Again, no calculator. Let me know if you have any questions. If you have any questions tonight, feel free. You can send me a text remind, and I'll try to respond to you. But yeah, hopefully we can take the time tonight to use that test review as a mock test. And then tomorrow, if you have any questions, and get those questions answered before your test. All right, come get your phones.
Question. Like the